Okay, let's start. Good afternoon, everyone. I'm Hyunho from Seoul National University. Today, I will introduce our work titled The City That Never Settles, a simulation-based LiDAR dataset for long-term place recognition under extreme structural changes. This work was conducted with my awesome teammates and Professor Ian Kim. In construction sites, place recognition, PR, plays a vital role in the maintenance and monitoring. Robots deployed on sites need to recognize revisited places in order to update maps, detect progress, and navigate reliably. However, construction environments are constantly changing. As shown in this example, between May and July, the same areas, place A and B, undergo noticeable structural changes. On the right, the point cloud visualizations clearly show that entire building blocks are added or removed over time. As we can see, localization and place recognition become particularly challenging in these conditions. Unfortunately, most existing PR algorithms assume a static world or only minor variations, while construction sites demand resilience to large-scale and ongoing structural changes. Here's another real-world example. On the left, we see this scene from the year 2020, an empty lot and an open street. On the right, the image shows the same scene in 2023 with a new building constructed and a traffic sign newly added. Thus, this illustrates an important point. Construction activities reshape the entire cityscape, ranging from roads, landmarks, occlusions, and practically all navigable spaces. And these transformations severely impact the performance of LiDAR-based localization and place recognition systems. However, existing datasets did not capture these types of changes well. For example, the Boris dataset mainly reflected seasonal variations such as weather and lighting. While the NSS benchmark does capture drastic spatial-temporal changes in construction sites, it was primarily focused on point registration and largely confined to indoor spaces. These benchmarks are valuable, but they fail to reflect the outdoor complexity present in real-world construction sites. Some datasets do track outdoor structural changes across time spans. For instance, the Oxford Radar dataset and Muirland Heliport dataset pair reflect changes over months or even years, including some structural changes. If we look at the chart on the right, which plots change rate versus observation frequency, we can say that these benchmarks lie somewhere near the diagonal, representing limited long-term changes. In contrast, our dataset targets the lower right corner, where large-scale transformations occur, and robots may revisit the scene only after substantial changes have happened, such as in construction or redevelopment zones. So again, the CNS is specifically designed to representing this challenging, underexplored region on the spectrum, which we believe that is crucial for advancing LiDAR place recognition in real-world urban robotics. So our key contributions can be grouped into three parts. First, we capture major structural changes at the city scale using simulation to emulate real-world construction and demolition events. This allows us to provide a challenging testbed for long-term place recognition in truly dynamic environments. Second, we introduce a new metric called TCR-SIM, or Symmetric Temporal Change Ratio, which ensures consistent measurement for structural changes regardless of source target direction. And third, we evaluate state-of-the-art PR methods on our dataset and show that even these methods suffer substantial performance drops under large-scale structural changes, highlighting the need for adapting to large-scale transformations. This slide shows how we model structural changes using color simulator. The timeline illustrates 4 sequential stages in the same map, from early construction stage in sequence 1 to a fully built environment in sequence 4. Gray points represent unchanged regions, and red points shows newly constructed structures, such as buildings, trees, and landmarks. This allows us to control the extent of change over time, simulating months or even years of development in a reproducible setting. To emphasize the challenge, here's a close-up example from the same location. On the left, you can see an earlier stage with only a base structure and sparse surroundings. On the right, in the later sequences, the scene has completely changed. This illustrates a critical point. PR methods will fail when it solely relies on local geometry, which is no longer preserved. Our dataset explicitly includes such examples to push the limits of PR algorithms. So let's talk about how we make this dataset. The data is generated in color simulator using the virtual autonomous vehicle. The vehicle is equipped with a 32-channel LiDAR modeled after the Oster OS1 and an idle IMU, which outputs clean, bias-free inertia data. Our sensors are synchronized at 20 Hz, and ground truth odometry from the simulator provides globally aligned poses for each frame. We generate data for construction and demolition scenarios. The image on the left shows a map where new structures are progressively added. The image on the right shows the reverse process, where elements are removed to simulate demolition. These operations are manually applied in the Unreal Engine editor, and sequences are recorded by driving autonomous agents along partially overlapping routes. Let's see this video again. Our dataset spans 4 distinct environments: Riverside, Suburbia, Downtown, and Metropolis. Each environment contains 2 to 4 sequences, representing different stages of structural changes. Here shows trajectories used in each sequence. We designed these paths to be partially overlapped each other to allow enough revisits, while still capturing different viewpoints. This slide shows the corresponding point clouds, color-coded by structural changes. As you can see, Metropolis in particular exhibits dense and significant modifications, making it an ideal stress test for long-term PR. Next, quantifying how much the world has changed is crucial for systematic benchmarking. To objectively measure structural changes, we adapt and improve the metric from the NSS benchmark, called the temporal change ratio, TCR. The original version compares the ratio of unchanged points, the set O, and the convex hull region, the set H. However, it is asymmetric. The value you get depends on whether sequence A is the source or the target. To fix this, we propose the TCR sim, which takes the union of unchanged points and convex hulls from both directions, A to B and B to A. This makes the metric order invariant, ensuring consistency across experiments. Here's a visual comparison. On the left, we visualize the set age from the original TCR definition. Sequence from 1 to 4 gives a certain score, but reversing the direction changes the value significantly. On the right, we show our symmetric version. By unifying two sets from both directions, it gives us a consistent measurement. And the table here below shows TCR sim values with our 4 maps: Riverside, Suburbia, Downtown, and Metropolis. For comparison, we also include the KAIST sequences, which includes 4 years of real-world changes. Remarkably, our Metropolis scenario reaches the value of about 0.3, which is even higher than that in the KAIST. This demonstrates that our dataset captures even more extreme transformations within a reproducible setup. With this metric, we now have a way to quantify and compare structural changes, making CNS not only visually rich, but also analytically grounded. Finally, we evaluated 4 representative LiDAR place recognition methods on our CNS datasets: Scan Context++, Solid, Ring++, and VTC. As you can see, performance decreases as TCR sim, which means time intervals, increases, meaning the more structural changes occur, the harder the problem becomes. This shows that the current methods struggle when facing city-level environmental shifts. Let's now look at precision recall curves. One interesting observation is that BTC maintains relatively stable recall value across different time intervals. This is likely due to its use of the descriptors from the submaps, which preserves some level of geometric consistency despite of changes implemented. However, its absolute accuracy remains modest. In short, BTC is resilient, but not highly accurate under large-scale transformations. In contrast, Ring++ shows the highest overall performance, especially in low change scenarios. These methods use bird's-eye view features, which may offer robust contextual cues over time. However, its performance also drops sharply as temporal change increases. This highlights a common limitation. Even well-performing models fail when faced with extreme structure modifications. To conclude, our CNS dataset incorporates large-scale transformations that go beyond what existing real-world datasets provide. We propose TCR sim to offer a fair, order-invariant measurement of structural changes. Finally, we present reproducible evaluations of leading PR methods, clearly showing the limits of current approaches in dynamic environments. We hope that this dataset serves as a stepping stone towards developing PR systems that can handle the long-term, highly variability challenges seen in construction and urban evolution. Thank you.
Open up to 1 or 2 questions. I have one question. In the data set, when you create different construction of different buildings and demolition of different buildings, what was the process of automating that process? Is there any human intervention or is it completely automated in terms of deciding that which buildings get constructed or demolished?
In fact, there isn't the automation process. I manually delete the buildings or trees and landmarks in the Unreal Engine editor. Yeah, and yeah, it's a manual process.
Do you think there's any potential for automation, or it's pretty much better to have a manual editing?
Could be, when utilizing the color Python API more expressively. But in my case, manually changing the map is more convenient, and that in that method, I can reflect my intention more exactly. Thank you.